Hi, I'm Peter, and I'm here with 2023 CIDR Gong Show champion, Conor Power. And we're going to talk to you about Lakehouse systems. So good. Lakehouses are an exciting new technology that combine many of the best features of data lakes and data warehouses. They're data management systems based on open formats, running over low-cost cloud storage, providing rich management functionality like transactions, data versioning, and indexing, while being accessible to multiple compute engines. That's a long definition, so let's break it down. Lakehouses build on low-cost data lake storage. So you're storing your data in a data lake like S3 or Google Cloud Storage. And you're doing that largely because it's cheap. You're storing your data in open file formats like Parquet. So your data is living in a lot of Parquet files in S3. You don't actually want to manage a lot of Parquet files in S3. So that's where the Lakehouse itself comes in. It provides a data management layer that gives you this management functionality like transactions, like metadata management, like indexing over your data in this huge number of Parquet files in S3. And it also makes this data accessible to many different compute engines. So it's accessible to SQL engines like Spark and Presto, but also to ML engines, to BI tools, to data science tools, and so on. So compared to data lakes, Lakehouses provide this rich management functionality like transactions and metadata management that lakes don't natively have. And then compared to data warehouses, Lakehouses make data directly accessible to any engine, not just the warehouse's own proprietary SQL engine, but any other SQL engine or any BI or ML tool that you care to use. So we're seeing Lakehouses are being widely adopted in industry. So we just heard about them for Meta, but they're also being used by Uber and Netflix and many other companies. They're increasingly offered by cloud data services like Microsoft Synapse or Amazon's EMR. And we're collaborating with Databricks, and we found that at Databricks, more than 70% of all bytes written by customers are to their Lakehouse Delta Lake. So even though Lakehouses are becoming really important, we think because they're very new, we think kind of understudied in academia. We think there's some really important design questions and research questions that we want to raise. So some of these include, how do you coordinate transactions over this low-cost cloud storage, which doesn't give you the primitives that, like the atomicity primitives that you normally would want? Where do you store your metadata and how do you query it? Assuming you want to have it in this low-cost cloud storage where your data also is. How do you efficiently handle updates, not just the big batch updates that data lakes do well, but also the point updates and upserts they don't handle well? And how do you do this without sacrificing read performance? So we're going to look in this talk, we cover all these in the paper, but in this talk, we're going to look specifically at the latter two. And to make it easier to study these questions, we designed LHBench, which is this new Lakehouse benchmark that we built on TPCDS. We're running it on the latest versions of EMR and Spark, which is a platform that supports all the different open source Lakehouses. And we've open sourced LHBench, and it's up on GitHub for you to try it. We're going to look at the three big popular open source Lakehouses, Hudi, Iceberg, and Delta. And we're going to look at a couple important aspects of their functionality. We'll start with metadata management. So metadata management is one of the most important features of these Lakehouses. So the metadata here includes the names and sizes of all files in a table, information on the contents of columns on the table, and so on. This information is really important because you needed to plan queries. If you want to run a query over a huge Lakehouse table, you have to know what files are in the table. You also have to know what files are relevant to the query. You don't want to be doing a table scan for every single query. So you have to know what files you have to read, what files you have to skip. And you need all this data to be really easy to read so you can do query planning efficiently. And native data lake metadata management is hopelessly slow, 1,000 keys per request in S3 list. So you have to build this functionality yourself. So current Lakehouses use two metadata formats. One is this tabular format used by Delta and Hudi, where for each data table, you also have a metadata table, which is placed in a well-known location in S3 per table. And then query planning is distributed. So before query planning, a batch job reads this metadata table and gets the information that the query planner needs, and then the query planner uses this to plan the query. Then the other option is a hierarchical format used by Iceberg, where table metadata is stored in a tree of manifest files in a well-known location. And then query planning can be done on a single node because you can use the upper levels of this tree as an index of the lower levels to minimize the amount of reads that a single query, that you have to minimize the number of files that have to be read to plan a query. So LHBench measures metadata management performance by running some high selectivity queries, which are computationally bottlenecked by query planning over TP-CDS data. And we're going to measure query planning time with different metadata management strategies over tables of different sizes, from 10 gigabytes up to 2 terabytes. So we're showing the results here. The x-axis here is the size of the table from 10 gigs to 2 terabytes, y-axis performance. We look at both query planning and execution performance, but these queries are very selective, so query planning completely dominates. What we find is that distributed query planning over metadata tables is slower for smaller data tables, but scales better to much larger tables, which is roughly what we expected.
Hi, I'm Conor. We'll be talking about the other 3 tests that make up LHBench, starting with update performance tests. So updates are a really important part of Lakehouse workloads, and they're challenging because they need to support both point updates and upserts, and Lakehouse workloads need to balance performance for reads and writes. So we see different Lakehouses prioritizing updates with like most recent releases for Iceberg, Hootie, and Delta, all adding new features for these, like deletion vectors, tombstones. There are 2 main strategies that are taken in these systems that users can choose between. The first is copy on write for updates. All 3 Lakehouse systems support copy on write. And in copy and write, it identifies files that need updates and then it eagerly rewrites them with the updates in the new files. And so this encourages write amplification at write time, as opposed to the other strategy, merge on read, which currently is supported in Iceberg and Hootie, and Delta is adding support for. So in this, updates are written to auxiliary files and then at query time reconciled. And so this encourages amplification at read time, but not at write time. And so we have 2 tests that exercise update performance in LHBench. One is implementation of TP-CDS refresh benchmark, which simulates maintenance for data warehouses. So with this one, we do 10 refresh rounds of 3% of the base data size. We run the TP-CDS queries after the initial data load and then after the refreshes are performed. We won't have time to go into a lot of detail on that during the talk, but there's more details in the paper. And then the other update test is a micro merge benchmark, where we directly compare the performance of copy on write to merge on read for the same storage format. And so for this one, we increase the merge size incrementally, scale it up, comparing the performance of for merge as well as for query after merge as the merge size increases. And so these are the results of a 100 gigabyte run on Iceberg version 1.1 for that micro merge benchmark. And so we see, what we expect to see is that copy and write performs better for reads, merge on read performs better for writes. In particular, on the left graph, we see it at the largest size, which is 100 megabytes merged in, the smallest is 100 kilobytes here. We see a 3x performance difference between merge on read and copy on write. And then on the right graph, for the query after the merge, we see at the 100 megabyte largest merge size, more than a 10x slowdown for merge on read compared to copy on write. I'll show quickly the results of a run on 100 gigabytes for the refresh benchmark. You should definitely check out the paper for more details on that. But as you can see, there's really wide performance differences between the different storage formats and between copy and write and merge on read in this setting. And then the last test is an end-to-end performance test, which is a 3 terabyte TP-CDS, where we load 3 terabytes of data. We measure the load time we run all TPCDS queries 3 times, and we measure the median performance time of the queries. And so these are the results of that run. For load, we see similar times for Delta and Iceberg, but a 10x slower run for Hootie. And this is because Hootie is optimized specifically for keyed upserts, not for bulk data load. And so, these are run on default configurations. And in the default configuration, Hootie is doing expensive key uniqueness checks and key redistribution on every update. And then for the query times, there are 2 main things that we attribute to the performance differences to. And I'll show example queries to illustrate those 2 differences. But we did see these differences across many of the queries. So Q9 is an example query where we see Iceberg is 10 times slower than Delta. And this comes from the fact that Iceberg uses a less mature Spark data source. And so it's emitting fewer metrics for query planning. As a result, getting much worse query plans here. This is an example query Q67, but we saw this in many cases where the just total amount of data read differs between the systems. And so Hootie is storing data in many small files, which results in worse compression ratios in Parquet. And so it ends up reading more physical data. So scans are more expensive in some cases, in this case, 50% more. In summary, we think that lakehouses are an important new and exciting systems, but they're still immature and there's a lot of research to be done here. So we've introduced LH Bench, which measures key lakehouse performance characteristics in some challenging scenarios in the hopes that it makes it easier for researchers to tackle these systems. And here's a couple of challenges we think are interesting in this space. How can lakehouse systems balance read and write performance? How can we increase QPS under concurrency? And how can we support transactions across multiple tables? So yeah, please check out the benchmark on GitHub, and the source TPCDS data is also available in S3 for you to access as Parquet files. Thank you.